Alright, so today I'm going to be explaining another important article with the title Role-Based Graph Embeddings. This paper in IEEE 2022, Role-Based Graph Embeddings. Random walks are at the heart of many existing mode embedding and network representation learning methods. However, such methods have many limitations that arise from the use of traditional random walks. For example, the embeddings resulting from these methods capture proximity, communities among the vertices, as opposed to structural similarity, which are the roles. So the embeddings are unable to transfer to new nodes and graphs as they are tied to node identity. To overcome these limitations, we introduced the Roll-to-Vec framework based on the proposed notion of attributed random walks to learn structural role-based embeddings. Notably, the framework serves as a basis for generalizing any walk-based method. The Roll-to-Vec framework enables these methods to be more widely applicable by learning inductive functions that capture the structural roles in the graph. Furthermore, the original methods are recovered as a special case of the framework when each vertex is mapped to its own function that uniquely identifies it. Finally, Roll-to-Vec framework is shown to be effective with an average AUC improvement of 17.8% for link prediction. So the goal of the embedding of an embedding method is to derive useful features of particular elements, vertices, edges by learning a model that maps each graph element to the latent d-dimensional space. While approach remains general for any graph element, this paper focuses on vertex embeddings. To achieve this, one possible definition of an embedding consists of three general components: the context function, which specifies a set of other vertices called the context C sub I for any vertex V sub I, such that the context vertices are surrounding and or topologically related to the given vertex. Each vertex is associated with two latent vectors: embedding vector alpha sub I and a context vector beta sub I. The conditional distribution, which specifies the statistical distribution used to combine embedding and context vectors. More specifically, the conditional distribution of vertex combines its embedding and the context vectors of its surrounding vectors, the modeled parameters, embedding and context vectors, and how these are shared across the conditional distributions. Thus, an embedding method models the conditional probability that relates each vertex to its context like this: x of C sub I conditioned on x sub I. X sub I is its attribute vector. So our goal is to model this probability of x C sub I conditioned on x sub I. Assuming the context vertices are conditionally independent. The most commonly used conditional distribution is the categorical distribution. A softmax function parameterized with two latent vectors is used. Thus, for each input context vector pair, we have this probability of x sub j conditioned on x sub I. And the summation in the denominator, if you look at that, contains many zero entries, and thus can be approximated by subsampling those zero entries using negative sampling. Because in language model we have, for example, we have scriptgram problem, then we have two alternative, negative sampling and hierarchical softmax, if you remember. So finally, the objective function of the embedding method is the sum of the algorithm of likelihood values of each vertex. So we want to map vertices to vertex row. The roll-to-vec framework starts by locating sets of vertices independent of the distance or proximity between any two in the set, who are placed similarly with respect to all other vertices. Thus, two vertices belong to the same set if they are similar in terms of structural features. We achieve this by learning a function that maps the n sub v vertices to a set of m vertex rows. Thus, phi is a function mapping vertices to vertex rows based on the n sub v times k attribute matrix X. Clearly, the function is a modeling choice which could be learned automatically or defined manually by the user. We explored two general classes of mapping functions. The first class of mapping functions are simple functions taking the form phi of x. So x is an attribute vector, and we used concatenation like sum to combine them. Intuitively, given a set of structural features, and suppose concatenation is used as a binary operator, then two nodes belong to the same row if they have the same structural features. This is consistent with the definition of structural rows. For further details, you can see this reference, 18. To make the different mapping functions more useful, we can first apply a feature transformation technique over the features. We can perform log binning on each individual feature prior to using equation 5. This has two main consequences. First, it allows nodes to be in the same row even if they do not have identical feature values. Thus, nodes that are sufficiently similar with respect to their structural properties belong to the same row. Second, log binning and other feature transformation techniques can be used to control the number of rows. The second class of mapping functions are learned by optimizing this objective function. This includes a mapping function based on low rank factorization. So we factorize x using this f of uv transpose. And here D is the loss, C is the constraint. They should be in C. That's our constraint. And R here is a regularization penalty. Then we partition U into m disjoint sets of nodes, where V sub j is a set of vertices mapped to a vertex row by solving the k-means. So now we want to talk about attributed random walks. Let x sub I be k-dimensional vector for vertex v sub I. An attributed walk of length L is just a sequence of adjacent vertex rows. Please note that this is very different from an anonymous random walk or any other kind of random walk. The roll-to-vacuum framework uses a vertex mapping function in attributed random walks to learn the embeddings. The third goal is to model the conditional probability that relates each vertex role to the roles of its context. Hence, the embedding structure is shared among the vertices with the same vertex role. Specifically, we learn alpha sub j and beta sub j for each set v sub j of vertices, which are mapped to vertex role w sub j. So Roll2Vec learns an embedding for an aggregated network where detailed relations among individual vertices are aggregated to total relations among vertex rows. The role embeddings learned from any method generalized by the Roll2Vec framework are also assigned to nodes or edges and therefore represent the class of structural node embeddings. So we focus on methods that are based on skip graph. Even the papers in anonymous random walk, they use the technique of skip graph. So this is the algorithm. For each v, we find the attribute walk and add attributed walk to S, and then you get stochastic gradient descent. But the way that you get this attributed walk is explained here. That you set the current node, you set of neighbors for node I, you sample it and append to S, then set I to the current node. Then again append, then another node, another row. So one possible generalized embedding approach using attributed walks is shown in this algorithm, Roll2Vec. We call it Roll2Vec. For simplicity, the generalized embedding method is called Roll2Vec. However, Roll2Vec framework notion of attributed walks can be leveraged by other researchers to generalize other important embeddings and representation learning that use traditional walks. So this is important. We show that Roll2Vec is inductive by nature, and more importantly, it can be used for more general graph-based transfer learning problem. Note that graph-based transfer learning is more general than inductive learning since it assumes embeddings are learned on one graph and transferred to another graph of interest, where nodes in the new graph may be completely different. So this is a simple toy example. The toy example shows only one potential instantiation of Roll2Vec. So step 1 computes the number of triangles and 2 stars that each node participates, whereas step 2 transforms each individual attribute using logarithmic binning. So step 3 derives roles using simple function phi, representing concatenation of each node's attributes values. And finally, step 4, here it derives a set of attributed random walks. Or let's call it roll sequences, which are then used to learn embeddings in step 5 that they actually compute the embeddings using skip graph that I mentioned. So this is the AUC scores for various methods for link prediction.